Hi everyone, my name is José Pissanha. I am researcher at the Brazilian Electric Energy Research Center. This work was made in joint with my colleagues Albert Melo, Roberto Caldas, and Jaume Falcão. In this work, we show a methodology for joint data cleaning of solar photovoltaic generation and solar irradiation.
A good forecast of photovoltaic solar energy generation depends on time series of measured data of good quality such as solar irradiation and energy generation. Measuring system failures and errors in data handling can corrupt data records with gaps and outliers. It is important that the feeding of solar energy prediction models must be preceded by a data analysis in order to detect and correct data errors. This presentation aims to describe the main features of an approach for the joint cleaning of measured data of global horizontal solar irradiation and energy generation using statistical techniques, data mining algorithms, and reanalysis data with the purpose of correcting outliers, replacing incorrect values, and filling data gaps. Failures in the metering and data handling systems can corrupt time records, producing three types of errors: data gaps, discrepant observations or outliers, and errors when entering registration dates. These plots show two examples of data gaps in GHI data. For this case, the proposed methodology will detect the data gap and fill in the gap based on reanalysis data. Now, we have two examples of discrepant observations or outliers. For this case, the proposed methodology will detect the outlier and correct the wrong registers. These are two examples of errors when entering registration dates. In the proposed methodology, the reanalysis data helps fix this problem. For all cases, the reanalysis data for the same days are used to define the sunrise and sunset hours and establish the timing interval for the GHI measurements. A good data handling methodology should be able to act only on unnatural fluctuations and avoid or minimize undue actuation on natural variations. To achieve this goal, the methodology proposed uses the combination of measuring data and reanalysis data. The strategy adopted in this work is the joint treatment of GHI and SPV measurement data. Given the strong dependence between SPV generation and GHI, the strategy adopted consists in the joint treatment of GHI and SPV measurement data. This figure provides an overview of the 5 steps of the proposed data cleaning methodology. The 5 steps are performed automatically. First, at step 1, we fit a linear regression model to GHI and SPV data. Next, at step 2, we remove growth outliers. At step 3, we will fill in the gaps. At step 4, we clusterize the GHI profile and remove additional outliers in the GHI data. Finally, we fit a new linear regression model to GHI and SPV data and remove the last outliers in the SPV data. In order to illustrate the proposed methodology, we show results from a case study based on data from a PV system at Monterone Giletti in Italy. The PV system is located in a car parking lot in the Salento University. The hourly measurement of GHI and SPV generation cover the period from April 1, 2012 to December 30, 2013. In addition, the hourly reanalysis data for direct and diffuse solar irradiation in the geographic coordinates of the SPV system are provided by the Surface Solar Radiation Data Set (LOSET).
Initially, we compared the sunrise and sunset times in the measurement with the sunrise and sunset times in the reanalysis data. The inconsistencies at sunrise and sunset times are fixed by moving the measured profile until minimize the sum of the absolute deviations between the measured profile and the respective profile in the reanalysis data.
Next, a simple linear regression model is fed to the SPV generation data and GHI data. Then, null and negative records in the radiation measurements are replaced by the respective reanalysis estimates, and the regression equation is applied to estimate the corresponding SPV generation values. About 3% of the GHI data was replaced. These figures show the box plots for GHI and SPV data for each hour of the day. Special attention is given to the overestimated values of the measurement. The values above the upper fence of the box plot are replaced by the respective upper fence hourly values. As illustrated by the box plots, in this stage, the gross outliers were removed. Almost 3% of GHI and SPV data were replaced. Next, the days with data gaps between 6 a.m. and 6 p.m. are identified. On days with gaps exceeding 4 hours, the gaps are filled with reanalysis data. For days with data gaps up to 4 hours, a non-parametric regression method is applied to the associated GHI daily profile in order to fill in gaps with smooth values estimated by Lewis. In the case study, 175 days present data gaps between 6 a.m. and 6 p.m. Among them, 6 days show GHI data gaps lasting longer than 4 hours. Hence, for this case, the gaps were filled by the respective reanalysis data. The 6 cases are shown in the figure on the right. In the remaining 169 days, the gaps are less than 4 hours, leading to the application of the Lewis method. Two examples are shown in the figure on the right. This figure presents some GHI profiles with data gaps and their cleaned profiles. The original profiles in red, the cleaned profile in blue, and the lowest confidence interval limits in black. In total, almost 3% of the GHI data were changed. In step 4, a coronary map is used to form clusters in similar GHI profiles. Coronary map or self-organizing map is an artificial neural network with competitive and unsupervised training applied to data clustering. This figure is the coronary map. It shows all GHI hourly profiles classified in 25 clusters. The similarity between the profiles classified in the same clusters allow to obtain typical profile for each cluster, as well as to identify atypical profiles or outliers that may still be present. In addition, the outliers in a specific hour age are replaced by the corresponding GHI median. In this stage, almost 2% of the hourly data were changed. Finally, at step 5, a new simple linear regression model was fitted, where the SPV generation is explained by the cleaned GHI values. The SPV generation values outside of the 95% confidence interval are replaced with the estimate calculated by the regression model. 3.6% of the hourly SPV generation data were changed. This picture offers a first view of the result from the data treatment. Note that the gross errors have been eliminated in the clean data. This plot shows raw and filtered GHI hourly values in the 2 weeks analyzed. This figure provides a more detailed view of the effect of the algorithm for data treatment. Look the raw data in red and cleaned data in blue. The proposed approach was effective in correcting defective or missing data, however, without significantly modifying the remaining data. Note that in the 2 weeks analyzed, there are 3 gaps in the GHI data. All of them were filled. It is worth mentioning the noise removal as indicated by the smooth blue curve. In the same way, this plot shows raw and filtered hourly values of the SPV generation in the 2 weeks analyzed. Look the raw data in red and the cleaning data in blue. The proposed approach was effective in correcting defective or missing data, however, without significantly modifying the remaining data. The 3 gaps in the SPV data were filled. As illustrated in this figure, the smoothing of some hourly GHI values had little effect on energy generation. These plots show the cumulative distribution of raw and cleaner data. The similarity between the accumulated distribution indicates that the data cleaning procedure was able to make the necessary correction, but minimizing undue changes in the data. As expected, the GHI and SPV generation time series show a clear daily seasonal pattern indicated by the autocorrelation functions. Note that the data cleaning approach did not modify the autocorrelation structure of GHI and SPV generation. This work presents the main features of an approach developed for the joint treatment of measuring records of solar photovoltaic generation and solar irradiation. The proposed methodology is based on the use of reanalysis data, exploratory data analysis, cluster analysis, and non-parametric regression. The proposed methodology was illustrated with a SPV system located in the Mediterranean region of Italy, presenting good performance. The results obtained point out that it was effective in correcting defective or missing data, however, without significantly modifying the other data. The results encourage to apply the proposed methodology to other measurement data sets as well as an initial stage of solar photovoltaic forecasting methods. Thank you very much.